So our speaker tonight is Rick Weitzel. He is a researcher at VA Ann Arbor, which is the Veteran Affairs Hospital, a focus on ultrasound image processing. And he is a return speaker. He's talked before, and he enjoys kind of programming, especially using Python and scientific computing and image processing. And he's going to be showing us how to build a steganography app with Python. So thanks, Rick.
Thanks a lot, Dan, and it's good to talk to the group again. The reason I thought I could present about this is when you're beginning to learn Python, one of the best ways to learn is to try to have an objective. You want to build something, and then when you try to make it, you run into all of these obstacles, and in overcoming the obstacles, you learn how to create some functions or build a library or build a tool. And so a couple of years ago, when I was really starting to, I guess when I joined the meetup group here and I started working on Python, I was reading incidentally about steganography, which is the art of hiding a message in plain sight. So the idea is if you want to send a message to someone and you want to have that message be public, but most of the general population not aware of what's in there, and you want to send it to a friend, you may be able to encode it in a picture, for example, or in an audio file or something like that. And I thought, gee, that's a really cool idea. Not to do anything super spectacular in terms of encryption or anything like that. This talk won't be anything, on that level at all. But it's more along the idea of, when you were a kid and you wanted to secretly pass a note to a friend, and you didn't want the teacher to know what was in the note or something, that kind of innocent thing. So, as I was learning how to do this, I put together a library and saved it and didn't really do anything with it. And then when Dan mentioned a couple months ago, looking for another speaker, I thought, well, maybe I'll dust off that old library and see if it still works. And I'll use some more recent tools where I would take a Jupyter notebook and put some user interface applications around it and see if I can actually build an app out of it. And so that actually was pretty straightforward. And so I thought, well, it's probably worth sharing this information. So what we'll do is we'll talk about steganography, but mostly what we're going to do is learn what you have to learn to build, an app like this, which is to understand the different data types and understand arrays and what's inside an image. And so learning this helped me do some more image processing at work with my work on ultrasound image processing using a bunch of different tools. So why do we want to do this? As I mentioned, this is what we're going to build will not be a difficult algorithm to crack, and it's not intended to transmit confidential or sensitive information. It's intended to be fun and for basic learning of data types. One thing that I thought was kind of a fun thought, I don't know if this will ever get here, but I thought, it does bug me a little bit to see ads for things, and I don't know how Google has gotten my personal information to have these directed ads toward me. And I had this idea that, gee, if I just sent all of my messages to people in pictures of puppy dogs, and all of my friends could just decode the message, then I would just start getting ads about dog food instead of when you reach my age, you get ads popping up about all these different health concerns, and they pop up and they say, oh, aren't you worried that you might have this terrible disease or that terrible disease? And I think it's probably because Google has figured out how old I am, and so they figure I must be worried about, illness or something like that. So I just would like to get rid of some of those pesky ads, or maybe steer them in a different direction. Or I thought maybe if I just sent pictures of trees to people, I would start getting landscaping ads or something like that. So we're just going to learn about this, and we're just going to have some fun when we do it. So this is the picture that's on the introduction slide for the meetup group. Basically, I just took a snapshot of a pretty sunset, and we're just going to use this. We could use any image, but we're just going to use this image and understand what the basic building blocks of an image are, what the basic building blocks of characters are, and how you can represent these things similarly so that you can encode character images or characters within an image without changing the image very much. So if you look deeply into the image, you find that every little pixel is made up of 3 and sometimes 4 values. And images are encoded with different types of data, but many of them are unsigned integer 8-bit integers or 8-bit numbers, which go from 0 to 255. They have 256 characters within 8 bits. And so the colors are coded. For example, if you can see my, can you see my cursor on the screen? I hope so.
Yeah, we can.
So basically, if you look at this upper left-hand pixel, it has, there's a red, green, and blue channel, and it has a 255R, 182G, and 113B, and that's what gives it this color. The one on the upper right is 160/24/0, so it appears more red because there's less blue and green showing. And so what we're going to do is we have to figure out how we are going to encode a message into these pixels and do it in such a way that we don't change the color very much. So whenever you're, I guess this is something when everyone is trying to do a project, you sort of write out your code. Many people call this pseudocode, but what we need tools to be able to convert a message, a written message, into a string. And you'll see a little bit later why we want to convert that into a binary string. And we also want to be able to turn an image that's a 3-dimensional vector into a 1-dimensional vector so that it can be reassembled back into a 3-dimensional vector, but so that we can just grab a snippet of that 1-dimensional vector and call it, for example, a carrier segment. And we're going to basically insert the message into that carrier segment. And then we want to take that inserted message into the carrier segment and encode it into the image and then reconstruct the image. And we want to do this in a way so that the image changes very little. And what we want to also be able to do is we want to have our friend have the ability to grab that coded segment out of the coded image, the image that has the message in it, to be able to decode that image, and then to be able to convert that message or that coded image segment back into a message. So basically on this slide, what I've done is I've just outlined what I've created in a library, and not being extremely imaginative, I've just called this Steganography library, or StegLib. And this is up on a GitHub repository, so you can look at this code, later and stuff. So on all of this, all this I'll put up on a GitHub repository so that you can, play around with it and learn from it. But basically, these are not very complicated functions, and we'll dig into this in a little bit in a demonstration. But we've just defined a convert function that grabs a string and takes a string and separates the string in a for loop into each individual letters, and then converts each letter into a binary letter and puts those binary letters together. And those binary letters then, or those binary, that string of binaries is then used to encode the information into the carrier segment. So there's a prepare carrier segment function, and all it does is it just turns the image into a 1D vector and prepares a segment of the image so that you can insert your bits, your I's and your zeros and ones, and insert the message and then reconstruct the image from the coded message. So these are all very straightforward functions. They just use for loops to read and different conversion statements to convert data types from one type into another, and then to insert them into an image vector, which is a 1-dimensional image, and then reconstruct an image from that for viewing. So what do I mean by all of this? So the end result is what we want is we want to create an application that we can use. So this is basically the application. There's not much to it, but it's basically just a little web app It allows you to select an image from a directory that you're in. So if you can see the directory that we're in on this file, we're in a directory called images, and we have two images. We have a subset of this image, and then we have an image. I'm going to go ahead and delete the coded image file, and because it's going to create a coded image for us. And if we select this this image file, and I will mention that it's a TIFF image. The reason it's a TIFF image is these are already formatted to be a 256 or an 8-bit character image with 256 values. So we select that image, and we can put whatever text we want in here. I can say, hi, I'll just pick on Dan. Great to see you at the meetup. All right, and then if we insert that message, it gives us a read back of what that message is. If we go to our file, the message information that we have is basically it tells us that by inserting the message, the function has counted the length of the message to be 57 characters. And we put the message, we have to pick a start location to place the message. So if we start at I picked 42 because of Douglas Adams and Hitchhiker's Guide to the Galaxy, like in 42, but we can pick any value if you want. We'll just pick 45. We insert this message in, and then what we need to do is we need to be able to grab that message. So we get give the start location of where the message has been inserted, and we put the message length in. Okay, this message is 79 characters. That was left over from an old message. And then we will decode the message from the file, and the message that we get back is the same message that we put in. So the decoded message is the message that we just inserted into the picture, and the coded image is now back. This is the message that has the text in it. And there you will note, this is a big image, but there's really virtually no difference between the coded image and the uncoded image. So let's dive into how we actually did that.
Hey, Rick, can I ask a question?
Please go ask away.
I just am getting a idea of the scale, because you said 79 characters. And then I see that the image changed from 5 meg to 7.1 or something like that.
Oh, let me. So the image size should not change. Actually, interesting. I get 7.1 megabytes. That's interesting. Thank you very much for noticing that.
Well, I wondered if it will change a lot if you add a lot more text, or is it something that just is a threshold, and is it linear, non-linear? If you double the message, will it double the size?
Well, something, this is really cool. Let's just paste this a bunch of times, like a bunch of times, and we'll copy this, and we'll just insert this long message in. And now our message is, let's start at 42, just because I nod to Douglas Adams again. Now our message string length, we've got 186 or 861 data points, and so
that's in there already.
That's in there already. So let's just look at this.
And is it refreshed?
Did I insert it? Oh, let's see. Binary messages inserted. Okay, let's just do 871.
861.
Okay, yeah, we'll do 871 just to see what happens. Oh, I started at 45. Look, as we get garbage if we start at the wrong place. So that's interesting.
Interesting, yeah.
So, all right, I wanted to do that at the end to just show folks what happened if you tried to break the program.
Oh, look at that.
So here's all the image just all came out again, and this one still was 7.1.
So that
megabytes.
It's just a sort of a threshold. It
May
just
just be-
bumps it up a certain amount.
Yeah, and it may be just the way by changing it to a one-dimensional vector and then changing it back and doing some things, it may just increase the size of it. So that's an outstanding observation. So thank you.
Well, thanks. All right.
No, that's tremendous.
Also,
That's
there
tremendous.
could be a set limit up to which you can the message can link.
Yes. So the length of the message is going to depend on how many pixels we have, and I'll show you how we're converting this into binary numbers, and we're going to be inserting the message into the very last bit of the binary data, so that the message color only goes up and down by one value, so that it really can't be detected with the naked eye. So it would have to be less than 8 times the length of the number of characters would be the number of pixels that would be in your image. So fortunately, most of our letters are pretty short compared to the number of pixels that there are in an image. So you can actually pack a lot of data into this file. So let's look at the decoded image again, and I guess that's where I pasted it, so that's not fair. But so let's dig into how we're doing this. All right. So what I've done is this is up on the GitHub repository, but let's just look at some of these functions and how they're operating. So I've just imported several libraries here into this Jupyter notebook. Just the Steganography library that we made, and I've called it SL, and then many of the conventional ones that people would be familiar with. So matplotlib is a very popular plotting function that we'll use to generate images. NumPy is a numerical Python library that is used to manipulate arrays, and then the operating system input-output. Pillow is a library that allows you to grab images of a variety of different formats, so we can read the TIFF image. And then for the user interface, these are just IPy widgets are the tools that we use to make the user interface. So if we just look at the, I'll start down here where we have the kind of a little teaching section of the notebook started. So we're just going to look at a list of the files in the directory that we're in right now. So these files are all uploaded on the GitHub repository, but we have a requirements in a virtual environment that's running and so forth. But we have this images folder. And so what we're going to do is we'll define our file directory. This is all done in the user interface. So we don't have to do this except for the teaching, for going through this sort of exercise right now. But the directory that we're going to look in is images, and we're just going to find strings, substrings that are TIFF images. And the widgets define the values in a selection function widget. And so I've just defined the name of the TIFF image that we're going to use. And we use the pillow image function to open the array that is the image. And we use NumPy to just grab that array and put it into a format that can be easily shown using matplotlib. So that's what this is basically doing. I had mentioned that many images have 3 colors, and some of them have a 4th channel. They have an alpha channel, which is how transmissible that pane is for sort of the opposite of opacity. So many times this is all set to 0. So if you use this channel and you start manipulating the number, it could be a clue that your image is in there. So we're just going to use the RG and B, the color channels, and not the opacity channel. So in this code block, I just execute this by doing a shift return. So I've executed this code block, and now pixel array is an array that we can image. And this is just using matplotlib to show the image that we're starting with. So as was mentioned, these images, we have to know how large the image is to know how much of a message how big of a message we can stick into the image. So I'm just going to grab a very small snippet, just about a 50 pixel by 50 pixel snippet from around 400 in this region up here. And we're going to just look at what that looks like. So here's, we've zoomed in to this sort of a character up in the 400 XY coordinate range. And you can see that there, this image that's very small, we call this a zoom. I've just named this zoom in pic, okay? And so this printing zoom in pic shape gives us, Y and X and the number of channels that we have. So if we just multiply these values together, this small, very, very tiny image here has 7,500 pixels. So because I've forgotten how to do math, we'll divide that by 8. So we can put 900 characters into this image. I'll show you why I got that 900 number in just a minute. But just to answer the question of how much text can you put into the image, it's quite a bit. So the image that we're starting with is actually cut way down from a large image of a sunset. So what I want to do now is zoom in even more so that we can illustrate how we're going to insert some text into an image. So all I'm doing is slicing, a few pixels from this array, and so now we have a 4, 1, 2, 3, 4 in the Y value by 8 in the X value. So 8 channels in the X value and 3 channels in RGB. So our image is 4 times 8 times 3. So if we just look at 1 pixel right now, so I've just looked at the upper left pixel. This is the value that I mentioned at the beginning of the presentation. This pixel is painted with 255, 182, 113 RGB. So what we want to do is we want to place characters in this pixel without changing the color very much. So the idea, originally, as I was thinking about this, I didn't know that people converted things to, their binary values, and then they hid the information in the last bit. So I started to make my own, alphabet conversion, and tried to change these values, by small numbers. And then I ran across an idea that other people very commonly use, where they just use binary values, and then they only change the last bit to encode the image. So let's look at how we might do that. So in order to do that, we're going to have to understand the differences between different data types. So there are, we all, I think, are familiar with strings. So these are the characters that we commonly use. Many on the meetup may be familiar with, there's an ordinal function that basically just orders the string values from 0 to 255. And so there are a lot of values, some of them are blank, but there are a lot of values that are just encoded to mean the different values of the characters that we use. And these are not only the characters that are letters for typing, but they're also carriage returns to get a return and things like that. I'll show you what this means. If we were to define letter 1 to be just a carriage return or a new line for print, and letter 2 to be N and letter 3 to be A, and we were to just use this ordinal function to look at what those values are, we would find that the carriage return, or the new line for print, is converted to a 10, and the N is converted to a 110, and the A is converted to 97. These are lowercase. So to just look at some of the common values we have, if we look at 0, 1, 2, and 3, and look at their ordinal values, and we look at capital A, B, and C, and we look at lowercase a, B, and C, we see that 0 is located at this spot of 48, 1 is located at 49, 2 at 50, and so forth. So, if you can just imagine if I, just going you would expect that, since 3 was 51, if we did, oops, we did board of 4, one would hope that we would get 52. And sure enough, we get 52. All right. So how do you get a string back? There's an inverse operation, which is just the character operation. And so what that allows you to do is to take any of these ordinal values and convert them back into a character. So you can see that 48, in fact, gives us 0. These are all coded as strings. 0 is a blank, and 10 gives us back the carriage return. 33 gives us a pound sign, and so forth. So you can just look. There's a whole bunch of sort of odd-looking characters, like 255 is a little bit of a strange-looking character, and 254 is another strange-looking character, and 253. So there's a lot of encoded characters in these numbers. So if you just took a picture and you broke them into their individual pixel values for an 8-bit integer, you would, and read them, you would get a whole bunch of arbitrary characters that included the characters that are in the English language, but also a bunch of additional characters, and some of them are blank. So now we can, what we would need to do if we really want to hide this integer or this message in the very last significant digit of the bit, we want to convert it into binary values. So there is this binary function that allows you to convert 10 into 10 in binary, and it has the coding of a 0B in front of the character to let you know that that's a binary value. There's another method of just formatting different letters, formatting the ordinal value with this binary code also allows you to just get an array of strings. So for example, letter 1, I think we had was 10, and that gives us the binary value for 10, just like it did up here. So if we were to take, the letter 3, and we looked at, say, we'll just call it something, right? We'll look at that thing. The letter 3 coded this value in binary. The ordinal value for letter 3 was 97, and the actual character for 3 was A. So now with this information, you can see how we can communicate back and forth between pictures and language. We could just use the ordinal values and insert those into the pixels of the image, but that would actually change those color values by a lot. And what we want to do is we only want to change them by a very small amount. So the way we're going to do that is that we're going to convert that picture all into binary values. And then we're going to take our message that's already been converted into binary values, and we're going to insert each digit of the binary value in the last binary digit of the picture value. And that way, the image, when we convert the image back into ordinal values, it will only go up or down by 1, because you'll only convert a 0 to a 1 or a 1 to a 0 in the last significant bit of the binary value. And the way to see this is that, well, let's call A binary. We'll just take A and we'll make a binary A out of it, and a B and make a binary B, and a C and a binary C, and so forth. And then the nice thing about these values is that they're all represented as strings. And you may remember when we add strings together, we just get a longer list of strings. So if we take this A, B, C, D and add it all together, this string that I'm highlighting here is a string of A, B, C all in binary. That's what we use to encode our message into the picture. So if we look back at our function that we looked at the very beginning, where we're going to convert messages and encode them into binary messages, that's what this steganography library convert function does. So now we have to go ahead and do the work of putting this image, or putting this message into the image. So let's look at what happens to these pictures. So if we just look at that single pixel, we saw that it had this kind of peach color. And if we wanted to look at any of the values, we saw that it was 255, 182, 113. We could convert each of those values to binary values as well. And so what we want to do is we want to take this last digit of the binary value and encode our message into that. Once we have done that and we read it out, we can take, for example, this binary ABCD up here. Remember, binary ABCD is this value, and use our function, the inverse function that we've created in our library to convert the message back, where it just counts every 8th character and converts that back into the message, and we get a decoded message from the binary message of our original character set. So I hope that I'm making sense here, but what this allows us to do is we can define any message, and we can use this convert function that we've made to convert that message into a binary message. And so hi there converts into this long binary string that has 8 characters. And what we'll want to do then is we'll want to insert that into the picture. So let's go ahead and start working with the images and see if we can do this. So we've got an input message value, and we'll say hi Python, or we can change this to hi team, just for fun. I hope I don't break anything. and we're going to take hi team, and we're going to convert that input message into a binary message. And we can see that this is the binary message, and it has 8 characters. Let's just change this so we can, we'll just actually put a couple exclamation marks there. Make sure that this is still working. Yeah, so we went up to 10 characters, all right. So if we take this, this very small picture that we looked at before, actually, let's create a picture of the same size. So what I wanted to do is, instead of having all of the different colors, let's just make it all gray. So I just used 150, and we've created an image that's the same size as the picture that we had before, that is all 150 for all of its values. And if we start putting the image in at the first pixel, and we can then insert the message using the insert message function in our steganography laboratory. And we get the length of the coded message is 8 times the length of the original message. So remember, that was 10 characters, so that's 80 characters. And the original data set from this image is all has all values of 150. If we look at the coded image segment, some of those values have been changed because some of the zeros were changed to ones. So we have 150, 151, 150, 151. If we look at the length of each of these segments, they're the same. And you can see the difference between these messages is really only one value. So what this is telling us is that our picture, all of the pixels will only change by one value. Now, the reason they're all positive is because they all started with 150, and that 0 can only change from a 0 to a 1. So I wanted to show you one more thing before we kind of conclude, and we can talk a little bit about this.
What does it look like? What does it look like?
So we'll show you. Okay, so all right. So This is the coded image. Thank you for asking. So here's the coded image. And maybe if you look really hard, you can see some 151s in amongst the 150s, but I don't think you can see anything different. Okay. So this image right here is the coded image, and it does have the values in it. But let's try to get that coded image segment out of the coded image. Yeah, this is a difference between the two segments. And we can plot the difference is basically black. But if we extract the image and we look at the code in the image, we get the message that we put in, which is hi team with 3 exclamation marks that we just put in. So so basically the image doesn't change appreciably. Okay, you really can't see the difference between one value. So the last thing that I wanted to just show you is that if we were to, we can use NumPy and a random number generator to just generate a random image. So this image will be different every time we generate. Okay, so I can generate it again, and the colors will change. Okay, so all of these colors are just random colors in here. And if we do the same thing with the image, where we insert the image and decode the image, you'll see that the values for the pixels, they're 144, 51, 183, 169, and these are 144, 151, 182, 168. So if we look at this difference image again, what we see is that the values will either be the same, or they'll go down by 1 or up by 1. And if we if we make a new random image, the difference matrix, if you will be different, because the values will either end in 0s and 1s, and we'll be encoding the message with 0s and 1s on a different base. So the change will be different. So all of this information is I put up on GitHub. I know I'm kind of sort of blasting through this. I probably should have planned. I hope this has been okay, an okay pace. But basically, all of these functions then, excuse me, are we've used them in the notebook to generate these widget functions where we can select a picture, and then this is the code to be able to generate, to insert our message here, and we can say, oops, add something here to our message, and we can insert that message into the image. And then this is how we generate a function that tells us where to start the image. Say maybe we want to put this at spot 100. So now we've inserted a 53 long character image or a message starting at location point 100. And if we want to decode the image, we need to start at point 100 and 57, is that what we said? We want to read the image, and I guess it wasn't quite 57. It must have been 53. Okay, so what we got is add something here and then a bunch of extra characters. If we're off by 1 and we try to decode the message, we're just going to get gobbledygook. All right, but if we go up by 8, an interesting thing happens. We lost the S because we lost our first character, but we got the rest of the message. So that's pretty much where I wanted to conclude and kind of just do a little bit of a wrap up and let everybody know these are the resources that I used to make this function. Basically, Voila turns these widgets into an interactive console or an interactive web app so that you can interact with some of the data on the back end. About 6 months ago, I gave a little meetup talk about using widgets in image processing. And there are several resource links here, and I'll put this up on the repository as well. And just
Rick, for a quick question.
Sure. Yeah.
I think I remember from that talk that you said that you needed to use Jupyter Notebook specifically because it wasn't functioning properly with Jupyter Lab. Is that that's
So-
true.
Well, thanks for asking that. I've just not gone back to try Jupyter Lab. So for this
Mhm.
application, I've just launched the notebook. Or the other way to launch, once you make an application, what I have here in my notes is, once you make an application, these last two lines, you can either start the notebook and then launch the notebook, or if you just type voila in the file name, then your application will come up as well.
Oh,
So
nice.
here, if you launch the Jupyter notebook, what you get is I'm hovering over the teaching file that we've
Mhm.
looked at, and I've also hovered over the Voila application. And so this is the Voila application. And
Mm.
you can either use a button in Voila, in the Jupyter notebook to
Oh.
launch the Voila application, or, and this is building the application right now. And so here's
Wow.
here's the application that we use. And then, or you can just from your command line, you can type voila, and then you can type the this file name, the new 5 voila app. I just, whatever, lack of imagination, that's what I named it. So
Thanks
so,
for showing that.
sure, absolutely, absolutely. So so I will put this all up on, I have some of it on GitHub, but I'll put the rest of it up on GitHub this weekend. And that's really what I wanted to show today. And just thanks everybody for listening, and thanks for being a great group. I've learned an awful lot from everybody that's given presentations here, and also the discussions. So I'll stop there, and I'm happy to take any questions.
Hey, Rick, can you please share your GitHub link somewhere?
Yeah, I thought I had it on my, I must have lost a line on my presentation, but I absolutely will.
Yeah, at least in the chat window, we can see that one.
Yeah.
Actually, I got lost somewhere in between when you were doing the conversion. So, but before that, maybe I can check into the code. But I was more interested in knowing, like, where exactly do you think like this thing will be used basically in practical world?
Yeah, so that's a great question. So I really did this for fun. Okay.
Yeah.
I really did this. I thought my work is to do ultrasound image processing. And a couple of years ago, when I really started to dig into the code myself, I thought I just need to learn this. And in order to learn something, usually what you need is a project to work on. And so that's why I wanted to work on this steganography project, because I knew that in order to do this, I would have to dig into, understanding the pixels and the image and things like that. This is the GitHub repo right here, and I'll paste the data. I for some reason, the image files wouldn't load when I, oops, let me get back here, stop sharing. I wanted to put in the chat the GitHub repository.
Yeah, no, I think it's such a good idea, like at least to save some some important messages or some important numbers, something there. But yeah, I think we need to have our own decoder as well, right?
Yes.
Built in.
Yeah.
Because
So,
if you lost that one, your images are no more good.
That's right. Yeah. So yeah, the idea. So yeah, you're exactly right. I mean, in order to really use this, you need, I would have a copy of the app. You would have a copy of the app. I'd write a note to you, and I'd put it in a picture, and I'd send you the picture. Maybe it's a picture of a dog, for example. And I would say, hi, don't you say Darnpie? Is that right?
You can call me DP, no
DP.
problem.
And I say, hi, hi, DP. Here's the dog. It has a 42 centimeter leg. Its legs are 42 centimeters, and its tail is 106 centimeters, or something like that. And then you would just know that you would stick 42 in is where the message starts, and then the message was 106 characters long or something like that.
Yeah.
It would just be concealed, but it's more, this is not serious,
So we are gonna be hired in the James Bond movie. So
exactly. Exactly.
Oh yeah, that's cool. Thank you. Appreciate that for sharing.
Yeah.
Hi, Rick. So I had a question.
Yeah.
You use this for your medical imaging kind of diagnostic computer vision and those kind of things.
Well, I use Python for ultrasound image processing. Most of it is what we call strain imaging, where we track data in the images from one frame to the next, and we try to look at how the underlying structure deforms. And so we're trying to detect mechanical information. That's what my day job is. Okay. So so this is just purely for fun, you know.
No, I also do you assist kind of the radiologist in this
Yes, I work with
diagnostic?
radiologists. Yes. Yeah.
Okay, okay.
So the people who are serious about this don't send it the way you've done it.
No, I know.
You put it in there basically as clear text. You don't need to know the beginning or the length to actually extract the message. You can get it out of there. But
Yeah, I'm sure there are very professional ways of doing this. This is just for fun. This is just
yeah. Well, I mean, one slightly different change is you have a reference image which the person has, and you alter it not by replacing the bit, but by adding the bit at the end. And so you would need to know that reference image in order to be able to extract the text.
That's an interesting technique. Sounds good. Yeah.
Yeah.
Yeah,
Also, it's probably the pillow writer. TIFF images have multiple extra data structures in them, and the pillow writer is probably adding some extra in. So I'm guessing that extra size is a thumbnail or another resolution that's sort of a fixed overhead. So I wouldn't worry.
Well, thank you, Roy. Thank you, Roy. I appreciate that. That's good.
Yeah.
Thanks.
Rick, there's a question for you in the chat.
Okay. Yes. So the question is, in effect, the messages are stored in the picture as a slight alteration in the color by changing the RGB values. That's correct. You know, and basically, I did not really research, as Roy pointed out. There are probably hundreds of ways that are much more sophisticated and elegant than what I've done. I heard that there was this thing called steganography, and I kind of poked around a little bit, and I thought I needed to try to make my own app for some self-education purposes. So I cannot recommend this as the best way to build a steganography app. It's probably at the lower
yeah, right. but I was just thinking, like, okay, in practical way, if this could be used as to build up something out of it. Like I cannot even think about it. Maybe same images being used as to for example, the medical records they were talking about.
Yes.
Why to separate files? Why to have the multiple separate files? Why not there is a way, like, okay, the same patient file can be attached, like, because there is a way now to pull out the information out of it without tampering the pixels and everything out of it. So something like that, or maybe any kind of, I'm not saying like, okay, only medical, but anything where the picture is holding its metadata, its message as well, so that the size will also be same, but information is more added into it. Like, because we are going through this stage, like where we are managing all these things separately, it will be more of like the one bucket which is carrying all the information about it, like when taken, who took it, who was there, because anyways that much, like, you can anticipate like 1,000 characters would be there at least, right, to have some description about it.
Yeah, that's a really interesting idea, DP. I hadn't thought about that, but yeah, like just incorporating the metadata into the last bit of the information or something like that in the image. Yeah. That's a clever idea. Yeah.
Yeah, and so another place this is used in real life is to watermark and output quietly. So if you steal an image from somebody, it has the origin from where it came. For example, TiVo. If you TiVo a recording over the air, it sticks in using steganography your serial number. so that if
Okay.
it gets out on the web, they can tell where it came from.
Wow. now
That's awesome. That's awesome.
James Bond right there. That's great.
Especially for the cases when, you know, like the images, the people, the photographers who are selling their pictures by their name, they know, like they will be sold this idea, okay, hey, we have the software which can be, you know, putting your watermark there, and just in case somebody, you know, claims that it's mine. No, it's
Yeah.
not yours. It's mine because I have watermarked it or something like that. I did. They can prove it. So that could be a project.
That could be a very good project. That's right.
Rick,
Yeah.
can this be used to create non-fungible tokens also? Do you see an application there?
I've only heard of NFTs and wondered why they cost so much. I don't know. Probably. Someone more knowledgeable should answer that question.
Any other questions for Rick?
Thank
It's
you, Rick. That's
wonderful.
awesome. Yeah, thank you.
Well, thanks to everybody in the group for all your great presentations too. So much appreciated.
Thank you. That was super cool.
Yeah. Thanks, James Bond.